So you only allow the negative one to pass through. This one, block, the negative pass through, block, positive, negative pass through, block, and negative one allowed to pass through. You see that? You only allow one of them to pass through. So that means this circuit lost half of the energy by simply cutting off the other half. Okay, so that half is lost as heat in the diode. So it's not a very efficient circuit, but of course it works. It can change your AC into a DC, no problem. Okay, no problem with that. Only efficiency, and normally this one become hot, and finally when it become too hot or after a long time of usage, this thing spoil and you don't have any power supply come out because totally cut off. All right, so that is called half-wave rectification. So we get something like this. So we're going to draw the half-wave rectification. What happened to the wave in more detail. All right, so we assume we take the positive side. So this is our AC voltage against time. Okay, and then this is our maximum of the wave, and this is our minimum of the wave, and here is our DC, and we only take the positive side. Okay, so now we're going to draw two waves here. Oh, this one not enough. Never mind, I can extend the axis here. Okay, so that is my second graph. Okay, our T is here. Hopefully it's recorded. Okay, can see, right? Alright, now our wave for the first one is this one. This is your first wave. Here is negative. Here, after that go to maximum again. This one, this one, this one. So roughly I draw freehand. I'm gonna get this, and here negative. One more time, one complete cycle. Okay, here. So this is our positive side, the negative side, positive side, negative side, and then with a time t, and this one is 2t, the period, which is related to the frequency by 1 over t. And then the maximum value here is Vp. This is negative Vp. Now let's assume our arrangement are like this. So like this, we assume that the positive one is allowed to pass through, this one gone. So that means we have 0 voltage here. Excuse me. 0 voltage here, and also 0 voltage the other side. This one also 0 voltage. Leaving only here is allowed to pass through. Right? So we have this allowed to pass through, this allowed to pass through. Okay? So something like that. Alright? So our value, of course, theoretically, it looks like Vp. But actually it's reduced a little bit because of voltage. Some of the energy is used to do work against the electric field and so on. So you might not get exactly Vp. You have to minus the voltage drop. What is the voltage? For example, if your maximum Vp here, the peak voltage is, let's say, V. Okay. So let's say the Vp is equal to the one that before passed through what we call that, diode. Let's say the Vp is, let's say, 12 volt. Okay, 12 volt. Okay, 12 volt. And that means this one is negative 12 volt lah. After half wave rectifier. Okay, rectifier. After half wave rectifier, the VDC, V prime, your V peak prime is actually equal to Vp minus the V diode voltage across the diode, which is 0.6 for silicon. So that means this one is going to become 12 minus 0.6, so you got 11.4 volt. Okay, 11.4 volt. Well, that is part of our calculation in Form 5. The most one is something like this. So that means if you want to produce a DC of 12 volt, you cannot use AC 12 volt because you're going to come out short of 0.6. So that means you have to do your calculation. You want to get 12 volt, you need to use AC of 12.6 volt so that you cut 0.6, it gives you 12 volt. Alright, so those are the common sense in designing the circuit. If you are using semiconductor diode such as silicon diode, if germanium, this one you cut 0.2. Alright, so that is our first type of rectifier, which is half wave rectifier. Alright, now we got problem with this type of voltage. You see, it go to maximum, go down 0, take a long time. This time here is 0.01 second, and then increase to maximum again down. So we call the ripple voltage. This is what we call the ripple voltage here. This one also the same. This is RIP. Never mind. RIP. Ripple voltage. Our VRIP is called the ripple voltage. Well, when your ripple voltage is very large, it's not good as a AC. This is the one that causes a humming sound. Okay, the humming sound, because you have power, no power, have power, no power, so your machine actually running with half of the efficiency. Well, the problem like this is going to spoil your machine much faster. So we must find one way to reduce this ripple voltage. Okay, so how do we reduce the ripple voltage? That one is actually the function of the next electronic component, which we call capacitor. Okay, capacitor. So now we go into capacitor and then look at how this capacitor help us in making the voltage become better compared to this. All right, so we look at the first next page, which is page number 8. The function of capacitor. So we have this one. Now we look at capacitor. Now our purpose of capacitor actually is something that is made up of two parallel plates. Okay, two parallel plates which are the same size. Okay, so with two electrodes. Okay, with two electrodes. When you connect these two electrodes to a power supply, the electric energy from the battery will be converted to electric field. That electric field is how the capacitor store electrical energy. And then when you connect these two terminals together, the current will flow, and you can keep doing it. That process of connecting the battery is called charging. When you disconnect the battery and connect this through to something else, that is called discharging. So we look at the symbol of capacitor. This is the symbol of capacitor. Because it is two parallel plates, so we have these two parallel plates, the same length, which is very similar to battery. Okay? Very similar to battery. So be careful when you draw capacitor, you have to make sure that the lengths of the plate are the same. So the symbol for capacitor is C. Okay? Stand for capacitance. Alright. Now, the unit to measure capacitance, C, is given by farad. Okay? F-A-R-A-D. The name actually derived from Michael Faraday. Okay? Faraday. So same like Newton, or the force in Newton, capacitance in farad, and so on. Now, we want to look at first our charging process. Our charging process means your capacitor must be connected to a power supply. Okay, let's say first one we use a battery, which is a DC power supply. Okay, so what happens is this: when you connect the positive terminal and negative terminal to a this one. So that means what happens is you're going to create a positive aluminum plate on the left and the negative aluminum plate on the right hand side. So that means you're going to create an electric field in between them. This is our electric field, okay, E naught, okay, internal electric field. Okay, this electric field will stay inside there theoretically without losing it, okay, without losing it. So this is charging process, okay, charging process. So discharging process is the opposite. Okay, the discharging process, during our charging process, we have current flowing in this direction, you know, from positive go to negative. So that is our direction of current. And then during the discharging process, okay, we disconnect the battery from the capacitor. Now your capacitor looks like a battery already, except it's not a chemical battery. It is not a chemical battery, but it is something like an electric field storage. Okay, your E naught is positive, 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 and negative here. So when you connect this charge capacitor with something, let's say a light bulb, okay, let's say a light bulb, or a resistor, let's say a resistor, okay, your current will flow now from the positive terminal to the negative terminal. That is what we call the discharging, okay, discharging, okay, discharging, right? So that is what happened during the discharging process, okay. Now that is a resistor. So that means finally the resistor will heat up because the energy lost into heat. But if you replace the R, okay, let's say you replace the R, the same capacitor, okay, the only difference is you replace the resistor with a light bulb, okay, with a light bulb. What happens is your light bulb will light up. So now we have our electric field, okay, like this, and then you connect, right? So you're going to have current passing through the light bulb, okay, the current. So it's going to make your light bulb glow, okay, but not for long, of course. The energy will be lost very fast, okay, it will lose very fast because the process of electromagnetic field collapse and disappear is in a very short time, okay, it happened in a very short time. All right, so that is the story about the capacitor. So that means we now know the capacitor actually can store the energy and release the energy. That is called the charging and discharging, okay. So now we look at how are we going to put this capacitor into our half-wave rectifier. So this is how we do it. So we have same AC power supply like the one before, okay, and then we have a diode, here, and then this is our DC motor, so that it run on DC, okay, and then this is our diode. All right, now our diode now, you can actually do something like this. You can connect, okay, you can connect this capacitor to a diode like this, okay. So this is our diode, this is our capacitor. So when you connect like that, what happens is we are going to compare the voltage drop, okay, the voltage disappear, okay, the voltage disappear by using this. We take the positive side, okay, we need to draw two, so I'm going to use this side here. So our voltage changes is here. This is the one that is before. Okay, before you connect to the capacitor, we draw more wave here. The purpose is to show you what happened. One is unregulated, one is regulated. Okay, so this is our positive side of the wave. Okay, so we know that this part here is 0, right? Is 0. Initially it is 0. I'm going to use the orange color one. 0. This one also 0. Here supposed to be 0 lah. This one is, sorry, this one is totally 0. That one we know. Totally 0. And this one has a maximum value here. So this is our maximum value. This is a maximum value after we go to 0. Okay. 0. Go to maximum, after that go back to 0 again. So this is what happened if we connect only one diode without a capacitor. Now this one, okay, it won't become totally 0 thanks to the charging and the discharging of our capacitor. So this one is the maximum voltage that you can get from the system. So where is our maximum? Our maximum is supposed to be here, right? This one is supposed to be the maximum. Okay, so we draw up to the maximum, and then it's supposed to come down, okay, up to here to 0 again, and then after that go up again, okay, like that, and come back to 0 again one more time. It's supposed to be like that, but because you connect a capacitor, what happens is when your voltage, the DC voltage increases up to here, because your capacitor is connected parallel to your diode. So that means your capacitor will have the same voltage together with your diode together because they are parallel. So that means the voltage will follow. But when the power supply voltage started to reduce, okay, when it reduces, because your capacitor can store the charge, right? Your capacitor don't lose the charge immediately. It will discharge. You see that everything here are going to 0 here. Nothing from the power supply. So that means the capacitor is going to discharge slowly. It's going to discharge slowly now. As a curve. It's a curve here. But normally quite shallow curve lah. Okay? It will discharge slowly until the external power supply increase again up to a certain value higher than capacitor. Then the process will repeat again, and then it will charge to maximum again, and then discharge again like this one. So that means this process is going to continue on until the next cycle come. Okay, so you see that where is the ripple voltage? Okay, our ripple voltage is between here and here, the highest point and the lowest point. This is now our ripple voltage, the VRIP. Okay, ripple voltage. So now the VRIP is our new ripple voltage. Okay, so now our ripple voltage is smaller. So what's the conclusion? If you have a smaller ripple voltage, it concludes that the humming sound is weaker or less humming sound. Okay, less humming. So that means it's more or less like a straight line. The larger the capacitor you have, the smaller is the ripple voltage. The less is the humming sound, the more efficient your DC equipment will function. So that means your motor, your DC motor is going to spin with less humming sound. Humming sound is a very annoying sound, you know, you don't like it. That sound is something like things going to spoil, okay, something like that. So this process is called, okay, the process where a capacitor, okay, reduces the ripple voltage, okay, is called smoothing effect. Okay, smoothing effect. It makes the voltage become smoother. Okay, make the voltage become smoother. A smoother voltage will have a very small ripple voltage. Okay, so now you can call this power supply now. This DC power supply. Okay, this DC power supply is now regulated. So regulated means it become more uniform. Okay, so that is the purpose of capacitor, to smooth out our rectified voltage or to regulate the output voltage. All right, so with regulated power supply, equipment work better, more efficient, and less problem. Okay, less problem. Okay, so now that is our half-wave rectification. Okay, half-wave rectification. Of course, this is the simplest circuit to convert AC to DC. But we have a better circuit than this one. Okay, that one is our full-wave rectifier. Okay, the full-wave rectifier. So that is our second application. Okay, our second application B. Okay, there is our second application B. This is page number 9. So B is the full wave rectifier. Okay, full wave rectifier. So full wave rectifier is definitely much more complicated. So no matter how, you have to memorize the circuit. Okay, you have to memorize the circuit. Okay, so we have a diamond shape. Normally it looks like a diamond shape lah. So we have this. Okay, I'm gonna draw much larger so that is clearer in the video. Here, this one is 1.5. So here, okay, and then here also 1.5, and then up to here is 2.5 lah. All right, so our diode is going to be in between here, and another side here, same thing. One and a half. This is 1.5. Same thing, 1.5, and also 1.5. Okay, these are all connected. So this is our diode. We want our diode to allow okay, so we have diode 1, 2, 3, and diode 4. Okay, our power supply will be connected to here. Okay, it's connected to these two top. So our AC come from here on the left hand side. Okay, this is our VAC. Okay, our AC power supply. Okay, now our output will be from these two parts here. Our output, and this one is our output here, and then we put a capacitor here in between. Now we already know the purpose of our capacitor, and this is whatever you want to connect to. We call the load resistance. This is your equipment. Okay, we call R load, and this one is our capacitor. Okay, this one is the capacitor. the C, and we have 4 diodes, and we have AC power supply. Alright. So now, how does this thing work now? So before that, we need to look at the wave. Original. This one is full wave rectifier without capacitor. This one is with the capacitor. Okay, with the capacitor and without the capacitor. Okay, half a wave, one complete wave, 1.5 second wave. Okay, this is the time, and this is our AC voltage, and this is our VDC, but not regulated, non-regulated. This one is our DC voltage, but regulated. Okay, our voltage here, the negative maximum, positive maximum, V peak. So here we only have the positive maximum. This one also here, positive maximum. Okay, so our first voltage here is a AC, negative here, positive again, negative again. Okay, this is our AC voltage. Alright, so this is a positive side, and this is our negative side. So what happened is, now we look at the way the electricity flow. Now first we assume the top one is the positive and the bottom one is negative, because AC changing the polarity all the time. 1 second 50 times in Malaysia case, because the frequency is 50. So our assumption is the one at the top is red, positive and negative. So I use a red one for the first one, right? So when it is positive, current started to flow from here, go to this connection point. When it go to this connection point, you see that it can only pass through D2, but D1 is reverse bias. So it passed through our D2, and then what happened is it passed through here. The next thing is it cannot go here because it was blocked. So it will go through this one, go through the RL in this direction. See that? It go down in this direction, and at the same time charging the capacitor. So now your voltage of capacitor is going to be the same as RL. And finally, it will go back to the negative terminal. It don't pass through this one because current